Yay.
You said corrections would be Friday, does that mean we should just, wait, should we just hand them to you either on campus or?
Oh, sorry.
Online.
I keep on thinking 3 days a week. No, so let's go next Wednesday, because next time I see you. Yeah, next Wednesday corrections are due, because there's no school. There's no school Monday for sure, right?
I think.
For sure.
Oh, I see.
Is it the 19th or the 18th? I don't think it's till the 18th because it's.
Yeah, we don't have school yet.
Okay,
No, next Wednesday, not this coming Wednesday, as in 2 days. but-
correct, yeah, week in 2 days.
Okay, thank you.
So I give you guys a little bit of time.
For the schedule online, is that, where is that again? 'Cause is it through the Google Doc thing you said at the beginning?
Should be Google Docs. If you go on a Weebly site, it's going to be after lectures. And it's the first thing. It just says Google Doc or schedule or something like that. Yeah. And I didn't look at it over the weekend. I should have updated it. So it may be off just a little bit, but I'll look at it today because I want to update stuff. We're good?
Yeah, I just want to kind of. see what the-
Yeah, no, let's, sure.
I can look it up on my own now. then.
All right, so schedule is updated. You guys should see it there. We're gonna jump to something that Sadie asked about the other day. So I figured, like, well, let's just do it. Proof for the chain rule. I guess we should do that here since we're looking at proof. This one does not have an eraser, so I'm using a different pen here. So I have a proof of the chain rule. So if I make a mistake, I'll have to scribble things out and then redo stuff. Okay. So I guess we did proofs for everything else, right? So I guess we should continue the piece here. So let, I don't know, H. What H of X is equal to F of G. Will that work? Boom. Right? So prove, and here's, at least we know what we're trying to prove, right? Because we've done this already here. We're going to try to prove this. And we'll get into some application questions here. So I'm trying to prove that you take the derivative of the first of our outside function, you multiply it exactly times the function itself of the second function, right? No changes, and then we multiply by that one. Let's jam. So if that's the case, then I'm going to go with limit, right? Limit as h goes to 0 of, and this is the fun part to begin with here. See, no fun. Let me.
Sorry, is that as h goes to 0?
As h goes to 0, Dun, da, da, da. I think it's going to be this, right? Plus h, we're good there, minus, because it's the inside of the function itself. Agreed?
Why? Oh, yeah, I guess that's.
1 second, let me check. I'm gonna scroll real quickly here and scroll back. Ha ha ha. Because I have the proof on the other slide here. Okay, forget what I just said. Okay, let's do this. It's gonna be this one right here, not this little parenthesis. It's gonna be the
Oh, it is.
the variable itself. It's inside all over h. So how about f of g of x plus h on the outside? Cool. Okay, and a little trick. Of course, there's some tricks here. So what we're going to do is we're going to do this here. We're going to write g of x plus h minus g of x all over g of x plus h minus g of x. Am I able to do that? Absolutely.
Wait,
'cause
how
I
do
can-
you, that's where I get mixed up, when you, every time it's like you multiply it by something and then it kind of solves itself out.
Uh-huh.
But how do you know what you're gonna do? Because
You don't. It's when they were doing it the first time, it was like, oh, that's a discovery. That's cool. You know, it's like when you find gold, then like, you know, hit this rock over here, right? Then you know exactly where to hit it.
ah,
So it's a point of discovery. You, especially with proofs. Proofs are such a thing where you, it's a light bulb moment. Like, oh, I could do this with it, and then all of a sudden it works out. Okay, so let's jam. I'm going to go with limit. I'm going to slow it down just a little bit here as h goes to 0 of that. And what we're going to do, we're going to have fun. We're going to slide this little guy underneath here. And we're going to slide the h to the outside.
oh. So that's 2 prime.
There it is. Yeah, the only thing is we do have to separate these out first. We're just going to go like this, and this will be f of g of x plus h minus. Okay, guys, talk to me here and tell me if you're keeping up with what's happening where. Limits, I can bring them across, is that right? Across multiplication. And voila, I know what this little guy is right here. So I think at least that is taken care of. Let's see, let's declare that being taken care of. So the front part is exactly the same. And the two quiet ones here, Taya and Kate, are you guys okay?
Mhm.
Multiplied by, there it is. That's the definition of derivative anyways, right? That's where our multiplication comes from. Now we got to mess with this guy here. That's the fun part there. All right, how do we do that? Well, we have two functions, right? We somehow have to get that g out of that sort of function there. And so when we do it, we just go like this. We're going to say, this is the other part of proofs here. I'm going to write k is equal to, I'm going to make that denominator in just into a single value. And that's the little trick over here. If I can make that into a single value, what nicely pops up from this? So let's talk about it. If this is k, but remember, we're still doing a limit function in our hands, right? So see if this makes sense. If that's true, that means there's the limit as h, and kind of this is off to the side. Limit as h goes to 0 of g of x plus h minus g of x. Talk to me here. That will go to 0 as well. Is that true?
Oh, so you can pretend that k is just h. You say we both go to 0.
Kind of, sort of, yeah. We're going to play that little game in just a second here, yeah. Okay,
And then-
everybody agreed there.
Mhm.
So, because h is going to go to 0, this guy's going to go to 0. So it's just going to be g of x minus g of x, which is technically 0 anyways.
Mhm.
So that means, that implies that k goes to 0, right? K, the limit technically is going to 0. Sweet, that's all we need right here. So now let's rewrite what we have here. So our front part now becomes this. It's going to be the limit as k goes to 0. Oh, one more thing we got to do. How about let's do this here. That also implies this. Yeah. How about this? I'm going to add this guy over here. So it's k. I don't want to add it this way here. How about this? The g of x plus k is equal to g of x plus h. Tell me if you guys agree there.
Wait, isn't the x?
Sure. Sorry, I kind of wrote it.
Oh, never mind, yeah, I see, because g of x minus g of x, then yeah.
I'm gonna add g of x to both sides, since that's what I've made it to be, right? And then I'm gonna just switch this around. I want it to be that g of x plus k is equal to g of x plus h. Are we good there? So it comes from me making this true. Okay, we good there. I think we're almost done. So then we say as k goes to 0 of f of g of x plus k minus f of g of x over k.
Oh. Wait a second. You, the parentheses, didn't you from? Oh, before we had it as g of x plus h. And now we have it as g of x plus k. Because k plus g of x plus g of x plus h. So we did mean to not have the h in the original like function parentheses for g. But now we have the k outside of it.
So we proved that the limit, notice we're over here. So this piece right here was the fact that we could say this right here. Because that k is going to go to 0 anyways, right?
Okay.
Then to undo our algebra is over here. So real quick here, let's talk about this here real quick. So limit as h goes to 0. Talk to me, see if this makes sense. This is the definition of limit, true? That's the definition of limit?
Yes.
Notice what we have here. We have the h's are here, right? H is the addition to what you're doing, right?
So it's just
And then it's just the two functions themselves. So notice what happens here. This is x, or this is k, right? And this is just the g of x being the same, right? You're subtracting the g of x from it here. So and then you say, oh, that is interesting because that is now just the definition of derivative of f of x multiplying the derivative of g. Are we good?
that was pretty cool.
Should we do one more? Yeah, we should do one more piece, then we'll get into some application questions, which I wanted to do. Okay, so there's theory. Next little thing is something called Leibniz notation. So Leibniz and Newton, they're the two people that came up with calculus simultaneously. Total argued who came up with what first. But eventually we went with like, oh, the other presentation that you guys can do is just the history of calculus, because it didn't cover as much, like the players in it. Leibniz and Newton, obviously, but even the build-up to calculus by I think it's the Bernoulli brothers. They also developed actually the limits and how you think of limits. And there's a few other ones that kind of just piece things together. And then it was like this aha moment when Leibniz and Newton were thinking about it. Okay, so you guys can do the history of calc as well.
Do you want us to tell you, like email you with our, what we're gonna do?
Please do, yeah. If you think of that, and then you could change it. I just don't want, the only thing I don't want is like 3 people doing the same thing. That's all. That's kind of looking out for. Okay, let's jam now. Leibniz. What a spelling of a name here. That's Leibniz notation. Okay, so when he came up with the calc stuff, he had a way to notate things, which is we actually went with his way. So that little prime little thing that we do, that's actually one of his notations. The other one was this whole concept of, and we've used it already before, but specifically inside the chain rule here. So we're going to go let h of x be equal to f of g of x. And u being equal to g of x. And, as that was not enough, y is equal to h of x, which is the same thing as f of u. So this is called substitution. You guys remember substitution? When did you guys do substitution in algebra? Oh yeah, when we did a very long time.
Was that algebra 2 or algebra 1?
Algebra. That's like pre-algebra substitution.
I think that was beginning algebra when we were doing elimination method, substitution method. Remember that?
Yeah. That wasn't pre-algebra.
That was algebra, yeah. That was just as soon as we got to that piece there. Okay, so here's what Leibniz says. If we take the derivative of h, we do that, it's technically, and he kind of just meshes all the pieces together. It's this one right here. If you think of this guy as being equal to y, so if you use this, you get the first one. If you use the next one, so the derivative, write it underneath here. Let's go f derivative g of x would be giving you the same thing as the derivative of u. Just this little piece right here. They're overlapping here. Which is really the same thing as dy du. And the last piece we need, so that's the second piece, and the last piece, and we'll get to what we need to in just a second here. And then this one right here. So that means that g prime of x would just be dy dx, sorry. That should be a dx.
Are the x and y's like subscript, like really small or something? Like, are they the same size as the d when you're writing it out like in print, or is it subscript?
No, it's same size. Mm-hmm. Okay, so I don't know that much about Leibniz that much, but it seems like he liked the whole concept of you write down on a chalkboard, right? And you see how things work together. You know, like same thing as here. He'll write a whole bunch of things together and he'll see, oh, that one goes to here. And if that goes to here, then this goes over here. And then he starts formulating everything. So I think we're ready. According to Leibniz notation, dy dx, which is from above, the same thing as the derivative of h, and we know the chain rule. Chain rule is this right here already. We know that. But if you put into this notation, we have ourselves a dy du multiplying with the class real quick here. I messed up just this guy here should be a u right here, right? Because notice from this piece here, it's u is equal to g of x. Should be du over dx. So this is du over dx. Okay, so just want to finish this up, then we'll get to ask some application questions here. Okay, you talk to me first of all. Is it a whole bunch of gibberish, or do you guys see connections that are happening here on things? So this is the first piece here. He just basically says, he puts in a y value and he puts in a substitution. And from there,
What's the point of all this?
It's just renaming stuff and then showing that it's still equal.
Yeah.
exactly. So when we get to the application, we'll get there, because what we're trying to do is we're trying to see if two things moving at the same time, we can separate them out. And so Leibniz notation in the calculus-based physics, we tend to go with his notation because everything is so parceled out, and you can see exactly which variables you're using when, and that's primarily the main reason why. And we'll get to one here. Yeah, I guess so. Let's just do one real quickly here. Leibniz notation just says this: if I'm taking the derivative of something, I can put it into two different functions, and then I can take the derivatives of each, as long as I know what I want u to be. So let's try. Let's do an example here. What example are we on from our notes here?
So it's class we end with like I.
Oh, that's right. That was a chain rule, right? So we're on example 2. Two class periods later. Okay, find the derivative. Using this guy's notation. Leibniz notation. All right, y is equal to, and let's go with x over 3x plus 2, boom, boom, to the 5th. Okay, so what we do is we're gonna part these into two different forms, and the easiest form is, notice you got the little x to the 5th power, right? It's the nestling of which function is which within each function here. So let's do that here. We're gonna do this according to Leibniz notation. We just do this. We say I'm going to substitute that form right there. We're good. I'm going to say u is equal to that. Makes things a lot more easier. And we could do the individual derivatives by themselves and then put it together. So if that's true, then this is true. Y is equal to u to the 5th. Everybody good there? And if that's true, tell me if you guys agree. dy du is equal to u to the 4th. Okay, that's one good thing. Next, let's jump over here. Now let's take this little piece right here. We say if u is equal to x over 3x plus 3, that means du dx would give us a chain rule. All right. Can you, I'm sorry, not chain rule, quotient rule. Can you guys do a quotient rule real quickly here?
3x is 1, the x would be 1.
Derivative of the first,
minus 3x Plus 2 minus 9, 3.
Okay,
There's just 2 over. Yeah, so it's 2 squared.
okay,
Let's not.
okay, are we good there? That worked out nice. Okay, so Leibniz notation says, I want to take the derivative of this guy, so then dy dx will just be dy du multiplied by du dx.
Didn't we just do what we were doing before, where you take the derivative of the outer and the derivative of the.
Absolutely, so notice what happens here, this is 5,
Just write it nice.
and I think I'm going to write it nicely in the next slide here, but that comes in as a multiplier. Technically, we've just done already, right? We just took the derivative of the outside, right? Kept the inside the same, took derivative of the inside. But what Leibniz allowed us to do is not to do it all at once, but to separate variables out, which that helped.
I guess that's a lot neater if you're doing a big complicated application.
If you're having 7 different variables in a physics equation, that just might help you out. Trying to
So is
figure
the
out.
other way Newton's way?
I don't think so. I think the other way, even though Leibniz did do the prime piece there, this one is just developed over time. I think it's just, here's the fastest way to do it.
There's just another way to do the chain rule.
Absolutely, yeah. Just another way to do the chain rule, more of separated out variables. Okay, I think we're good. Let's jump to just to have some applications here. Exercise 3. So love it. A train. If I can spell train, T-R-A-I-N. The train's position is given by S of t. Have to do a physics problem. 1, 2. S in meters. And t in seconds, of course. At time t equals 6. Find a velocity acceleration and train speeding up, slowing down. There it is. There's our physics problem there. All right, talk to me. How we doing? What we doing?
Should we, move the -2, that whole -2 power to the bottom when we're doing it? Or does it,
Sure, go ahead. Yeah, we could. It's gonna be 100 over t plus 1 to the second.
but
Sure, it'd
then
be
we can't
quotient
do
rule.
the chain rule normally.
Then you gotta do a quotient rule, chain rule inside a quotient rule, where here you can just do a power rule, which
Yeah.
makes it a little bit easier. And you got the 100 in front. Are we good? Anybody done yet? No, okay, so let's go with A. Okay. And you guys talk to me here, talk to me, because I want more of a conversation here. So remember, we say position is the top rank, right? Whenever we take a derivative, we jump into velocity, right? We take a derivative again, we're gonna jump into acceleration, right? So the relationship between position, take the derivative, you're gonna be in velocity, take a derivative again, you're gonna be in acceleration. So if this is the position function, and we want to know what's happening at time equals 6 seconds, that's all. So let's just take the derivative. So the derivative of the position is going to be our velocity function. That's cool. So I'm going to stick the 100 on the outside. Good there. And I'm going to go with multiplied by -2. T plus 1, what's -3, is that right? And then we're going to multiply times 1, which is just the derivative of the inside positions, all yours. Okay, so -50. At this point, I don't mind putting it on the bottom. Like that? We good there?
Yeah.
Cool. Okay, so we got our velocity. That's great. But then we don't really just want the generic velocity equation, right? We wanted a specific time. So then off to the side over here, I want to find the velocity at 6 seconds. That's what my goal is. What does it say? 6 plus 7, or 6 plus 1 is 7, 7 to the third power. $343, okay.
-0.146.
-0.146. Okay. Okay, now the fun part. Give me units for velocity. Good there. Velocity is per second. Okay, so that's interesting.
And then to find acceleration, would you say the derivative of the -50 over t plus 1 cubed?
Yeah, so go to the next level here.
Okay.
Okay, Taya and Kate, you guys okay? Cool. So let's take this guy, and then I'm going to change it again into, remember, we could either write it like this, or we could write it like that, right? It doesn't matter which way we write it. Just that second form is a lot easier to take derivative of here. So let's go with derivative of velocity, which is now acceleration for us. So -50 on the outside, and multiplying now -3 and -4 being multiplied by 1, simplified form would be 150 plus +1 to the -4. Are we okay there? I'm running out of room here, so I'm going to write it like this here. So either writing it like that or like this, whichever way, it doesn't matter. Both of them the same. Okay, talk to me here. We want acceleration at 6 seconds though, right? And who is in physics here? You two. Okay, you guys talk to me here as we do this one.
Oh, 6, 2, 5.
Ooh, okay.
Meters
What?
per second squared.
Sure. What's 7 to the 4th power? Just out of curiosity.
2,401.
Okay. Oh, and then what's the answer?
Negative point, or sorry, not negative, 0.0645, 625.
625. This is
Meters
going
per
to be
second squared.
perfect. Okay, so acceleration is that one right there. All right, so in talk to me for the same thing in physics here. So whenever we calculate stuff, remember with velocity, velocity is speed and direction, right? And so in math, we try to think about it's either go to the right or to the left, right? And so in this case, we're slowing down, speeding up here. So talk to me, velocity at 6 seconds, what's happening there? See again? Yeah, we're moving to the left side, right?
Or accelerate.
But then acceleration is positive, right? So speeding up or slowing down? Not to confuse you guys here. So
Be speeding up. Are we decelerating?
we should be decelerating. And the way we do it in calculus, and the guys in physics talk to me as well. If there's a difference of sign between the velocity and the acceleration, okay, that's when the slowing down is happening here, right? Because notice the velocity is going one direction, it's going towards the left,
Oh, it's
right?
counter.
But yeah, but the acceleration is actually going the other way, right? It's actually going towards the positive side. I think that's right. So let me just see real quickly here if I'm, because I know we do that with. See what Bob says, just in case. Yeah, and then I'll just read it here. So the train is slowing down since velocity and acceleration have opposite signs. That's it. So we're just looking at signs. Slowing down, and V of 6 is negative, A of 6 is positive. Okay, physics people, talk to me. Any thoughts on that one? It's almost like too simplistic, I think. It almost like it gets you like, hey, as long as I know the formula, boom, I just take the derivative, I plug in points and I'm done. No. I'm not sure if in NASA or SpaceX, when they launch something to the moon, if it's just that cold turkey, easy. I don't know, maybe it is. I should step into one. I don't think it is. There's a lot more
If it was,
propagation.
a lot more people would be launching.
Uh-huh. True, very true. Okay, example 4. So this is this is where it hits Leibniz notation in a better way here. So I got a few little things here happening here. I have you guys know this already here, but let me write it down. So formula for area of circle is A is equal to pi r squared. That's fine. Okay, suppose circle is expanding. And when we say expanding, we're talking about r squared is getting bigger, is that right? Or r is getting bigger, right? At the same time, a is getting bigger as well, right? Because those two have connections here. So boom. So how about this here? Suppose r is equal to 2 minus 100 over t plus 7 to the second. Find how fast is the area expanding. Cool. Sorry, it's chicken scratch here. So suppose that r is the formula for r is that right there. 2 minus 100 over t plus 7 to the second. Find how fast is the area is expanding. So we know what the formula for r is. We have two different formulas, and this is, I think, the genius of Leibniz right here, is he's able to separate things out at this point. We can figure out how fast r is expanding by itself. We can figure out how fast area is expanding. Real quickly, let me give you some context here to it. This is just out of curiosity here. A boat is oil spill in the ocean. We're good. And so you don't get a constant. So you have, as we look satellite images, we'll take a satellite image, right? We'll take another satellite image, and the easiest one is to compare radii to each other, right? So it went out this far, it went out this far, it went out this far. And then, so we can get a formula for, it's not gonna expand out perfectly, right? Every 2 seconds, it's not gonna do that, right? Because you have a spillage that's happening, and it's going out different directions. So the R value is gonna be very complicated, something close to that, right? It's gonna slow down as it's getting further out. And so now the question is, how fast is this area expanding? And we have 15 minutes to solve this. So all yours. What do you guys think? Give you a hint here. How about this? How about this? I think we can do this at least. dA over dt. Is that what we're trying to find? Over time? I think so. That is going to be predicated upon the fact of how fast dA is expanding of dr, and then also dr expanding to dt. I think that's the clue that's given. Like, oh yeah, that's right. Because I can separate those out. I have a T connection to R, and then I have an R connection to A. What do you guys say? So first things first, we have a formula over here on our hands, don't we? A is equal to pi r squared. So dA dr 2 pi r, you good? And it should lend you to some connections here too, as soon as you see that, like, whoa, hold on, it's a circumference, yeah. So we go from,
The area is just the circumference is the derivative of the area.
mhm. How interesting is that? Okay, so we have that formula, I think we've set there. Now we just need to figure out the other one, which is the more difficult one here. And running low on time here. So let's see, isn't that 2 gonna go away? Is that right? So let me see if I can bring this up. -2. Oh, we like that now, huh? We like bringing it up into a negative exponent. So dr dt is going to give us -2 goes to the front, multiplies it with that. Talk to me here. I think it's 200. T plus 7 to the -3. Good there?
Why did we get that?
So the 2 goes away because that's going to be a 0 anyways when we take a derivative, right? But then for the derivative, it's going to be -2 multiplying times the -100 for the power rule.
Where does the -3?
And then we always subtract 1 from the exponent after we take the derivative. X plus 7 to the 3rd. That's cool. I think I'm done. Is that right? It was so interesting. Reading. Do you guys remember it's called the BP oil spill in the Gulf of Mexico, right? A long time ago, the oil spill. It was interesting because they did studies over the years, and the oil, even though it wasn't refined oil, it was crude oil, right? Over the years, it actually did dissipate into that area there. So initially, yes, with birds being stuck in muck, right? And all that stuff. It was just, I forgot what it was. I think it was 2 years later, it was 98% dissipated into the surrounding ocean. So the salt water sort of ate it up or something. I thought it was interesting. Okay, what are we good here? I think we are set. So a dt, which is how fast is this area expanding, right, due to time. We have ourselves 2 pi. The original formula for the r value multiplied by the derivative and am I going to make you simplify it? I don't know. I think we'll leave it like that.
Yes. Much nicer.
Okay, are we good there?
So if you take the derivative of the value that r is until the end, because when you have that g over dr, you do d or dt, you need to change the r into the derivative.
Let's see, according to, this little piece right here, right, we got from here, except the r value is actually something. R value is this right here.
We can't just leave it as r. You have to actually put in.
Yeah, you put in the value because you want dt at the end. You want the according to change to
So
time.
Wait, so yeah, the 2 and the 2 is not under that fraction.
Cool. Okay, Eli said something which I thought that's kind of cool to sort of go beyond here. So area of a circle, which is the inside stuff, right, of a circle, right? When you go from there, you take the derivative of it, and what happens is it gets you the change of it is actually the circumference of a circle. So cool. Okay, so just a few minutes left here. Well, Jam, I'm going to give you this here. So this is, let's expand it out to 3D here. How about this volume of a sphere? Do you guys remember volume of a sphere formula?
Have you ever learned that?
I'm not sure if you guys ever did.
I think it's given on the SAT in like the beginning part, but I don't know if we ever.
I feel like we never learned it though.
Maybe used it in like lower grades.
Should have been, first time should have been in geometry class. Should have been the first time.
No chance I remember
Okay.
that. I don't remember anything.
It's a blur. So volume of a sphere. I think it's 4/3. I'm pretty sure. Pi r cubed. Cool, cool. Let's take the derivative of this guy. So it'd be what, dv dr, is that right? That would be an easy one. Doesn't require chain rule or anything.
That would just be 4 pi r squared.
Okay, 4 pi r squared. Okay, I'm gonna leave it like that. And if you're totally curious, you're gonna look up like, what? What is 4 pi r squared
4 pi r squared.
having to do with?
Is that gonna be like the area, like the outside of the sphere?
I think so, or something called surface area.
Area.
But you guys check with me and see if we come up on Wednesday, if that is truly it right there. Okay, and then one more thing, I guess we should do this here. It's use of chain rule with function notation. So what example are we on? Perfect, yep, thank you, 5. Boom. So we have h of x is equal to f of g of x. And then we have g of 1 is equal to 4. G prime of 1 is equal to 3. And f prime of 4 is equal to 7. And we got ourselves find that. So again, this is
How's the derivative of like, so how if g of 1 is 4, how's the derivative of that 3?
if g
When you say the derivative of g of x, it's something different.
just a value, right? Value of the derivative. So velocity at a certain point. Could be 4, the position is 3, or vice versa, sorry. Position is 4 feet above the ground, but increasing at 3 feet per second. Cool,
And
all right.
is that f prime of 4?
4, equals 7. All right, so let's go with here. So the derivative of h of x is going to be the derivative of f of g of x times the derivative of g of x. We're good there. Oh, sorry, don't need the equal sign here. So I got that, that's my formula. Now the question is, what is that, right? So we set up a generic formula. I'm gonna make sure you guys get up just a tinge early here. Ms. Bear, so she get in here.
Oh, So. So G, if we put in G of 1, then we get 4, and then we have to do F prime of 4.
I go with that here. So
Which is
G of
seven.
1
Yeah. And then G.
multiplied. So we just need we still need the original G function, right? We need position for G. We also need velocity for G in a sense, or a derivative of G, and then we also need derivative of F. So in that case,
Because
say again, Kate?
How do we know that inside the parentheses was 1 or X was 1?
Because we wanted this right here. We wanted
Oh, got it.
1.
So it's just
Oh, sorry.
1.
I think so, yeah.
that's not really a problem, it's just plug in the values and put them in the right order.
That's all. Just want to show you that was an easy one. They will, on the homework though, you do get a table of all these values, F, G, is it and H? Yeah, F prime, G prime, and then they'll have some, it's going to get a little more complicated than that because you're going to have H of X to be given not as just a formula like this, but on the homework, how about something like that.
Okay.
Okay, so it's going to get a little more complicated. Okay, with that, I'll let you guys out 3 seconds early.
Thank you.
All right, have a good Monday, and we'll come back on Wednesday.